Hello guys, nice to see you. How are we doing?
Hello, I'm
Hi.
fine. Thank you.
Hello.
And you?
Good.
How are you?
I'm doing well, thank you.
Good afternoon.
Afternoon.
Hi, good afternoon. Yeah, hello everyone. So, short recall of our previous discussion. We were discussing the, first of all, we introduced different types of materials in terms of their electrical conductivity. So we distinguished based on the difference in band structure, what is insulator, semiconductor, and conductor, and focused our attention on a conductor in electrostatic equilibrium. So we have shown that in electrostatic equilibrium, there is no electric field and electric charge inside the bulk of the conductor. So means that electric field is equal to 0 in the bulk, and there is also, if we provide some electric charge to conductor, it will reside on its surface without penetrating inside the bulk of the conductor material. So what's going on here? Today we proceed further with our course of electrostatics, and we will discuss in details, introduce first and discuss some features of electrostatic potential. So it's another parameter which can be very useful when we deal with electrostatics in general, like some electrostatic electric fields of different created by different charges, either point or continuum charges. So this concept of electrostatic potential is very important, specifically when we deal with work done by electric field. So let us switch to the slides and get started. So we know so far that if we place some charge, let's call it test charge, in let's name it Q0, in external electric field, there will be some force exerted on this charge. This force is called electric force. So electric force, electric force is equal to this test charge times electric field vector. So this is also vector. Obviously, if now we exert on this charge some external force, some external agent, let's call it, causes some displacement of test electric charge in external electric field, then electric field will perform some work on this test charge because there is some electric force. And this work which will be done by electric field will be negative to that work which is done by external agent, causing this displacement of electric charge. So when we deal with electric or magnetic fields that will be in the future, it is convenient to use such term as ds vector, which stands for a small displacement vector, which is oriented tangentially to the path of electric charge, in our case, in the space. So if we want to consider some work done by electric field along very small displacement, we can write the following. Work is equal to electric field force times this small displacement vector, ds. So we have a dot product of these two vectors, means that the result will be a scalar value and means that our work is a scalar. So if we write it further here, it will be Q naught times electric field vector dot product ds vector. So that is the expression for work done by electric field. And if we consider electric field, electric charge, like test electric charge system, as some isolated system, the change of potential energy of such system will be equal to negative of work done by internal forces of this system. So change in potential energy du is equal to minus work. We can highlight here internal work because this work is done by electric field. So this is work done by internal force of the system, electric field, test electric charge. And that will be equal to minus Q naught times E vector times ds vector. Okay, so we define how we'll change potential energy, but that is some small change of potential energy along a very small displacement vector, ds. So now we want to have some generalization of this situation, and specifically we want to define change of potential energy when we move this test charge in external electric field from point A to point B, and that could be quite a big distance between these points. So in order to do that, we need to apply integration. So change of potential, already large change of potential energy between these points A and B will be given as minus Q naught times integral from point A to point B, scalar or dot product of electric field vector and ds displacement vector. So here we need to mention one important thing, that this integration is performed along the path that this electric charge Q follows as it moves from point A to point B. Another important point here, since electric force similar to gravity force is a conservative force, this integral along path will not depend on the path and will be defined only by initial and final position of our test charge, means by position of point A and point B. So now, when we know how to define change in potential energy of a test electric charge in some external electric field, we can proceed further and introduce a new parameter, which is potential. So if we divide change of potential energy by the electric charge by test electric charge, we will get the potential. So V is equal to U, which is potential energy, divided by Q naught. So in each point which corresponds to potential energy U, we can now define potential V. And similar to potential energy, potential V is also a scalar quantity. And when we move from, so as I said, each point in space possess some potential energy and thus potential. If we move from point A to B, there will be some change of potential associated also with this change of potential energy. So there will be dV is equal to VB minus VA. Means final point potential minus initial point potential. So in general, when we have some general case of moving from point A to point B, assuming that electric field may not be uniform, because it can either be uniform, so it will not change neither its magnitude or direction while moving from point A to B, but it also not true. It can be position dependent. So in general case, we can write that in potential is equal to change of potential energy divided by electric charge, like test electric charge, and it is equal to minus integral from A to B times vector dot product displacement vector. So these are definitions of potential energy and potential in electrostatic field. What is important here to mention that it is critical to distinguish between potential energy and potential. So talking about potential, you can see here, it is defined only by the source of electric field and electric field itself. So that space where we want to deal with it. However, when we deal with potential energy, that we also need to provide information about the test potential. Don't need a test charge. Potential energy, we add information about test charge. So now when express work done by electric field test charge in terms of change of potential. So we can try it on the next slide. Case work will be equal to test charge times change of the potential. The units for potential are Joule divided by. So the definition of 1 volt can be related in the following way. 1 joule of work should be done to move 1 coulomb of charge through a potential of 1 volt, or this joule per coulomb. Yes, you have a question? You're welcome.
Okay, so would you show the last slide? As I see in Zoom, your internet connection seems to be poor, and so the quality decreased of slides.
Let's somehow I quite well, so it's it different from, so you said the quality of the image, you cannot see it properly, yes?
Yeah. Yes.
Let me try to switch it back and forth. Let's see if we have some improvement. Anything changed?
It seems you lost connection.
Okay, I'm sorry about that, but I believe not. I will try to write larger letters, so probably it will be easier to see that you mentioned about this. So let us discuss a bit also about these units. So we mentioned here that a unit for potential is joule divided by coulomb, and that can be yeah, it's actually written here that the internet connection is unstable. Hi, do you hear me? Are you still here?
Yes.
Yeah, we're glad to
Okay.
see you.
Yes, thank you for waiting. I'm sorry about this, but unfortunately, yeah, it just disappeared, the connection. So hopefully it will work now. Let's see. Does it look better or the same low quality?
A lot better.
Okay, that's promising. So let's continue. So we replace joule with Newton times meter, and here in the numerator we have Coulomb. Do you remember which physical quantity has these units, Newton per Coulomb? We introduced it at the early beginning. That's actually electric field. Electric field units, it's Newton per Coulomb. So now, if we substitute Newton per Coulomb with electric field, or we can rearrange it, we can say that that's so here in the left side we have potential. Then if we, let's write it here, potential is equal to Newton per Coulomb times meter. So we can write that Newton per Coulomb is equal actually to potential divided by meter, and that, if they are equal, that can be also written for electric field. So we have potential per meter. So means here we introduce for the first time these commonly used units for electric field, where we have potential per meter. And that gives us also some feelings of the relationship between electric field strengths and potential. So with that, we can claim that electric field can be considered as a measure of the rate of change of electric potential with respect to position. So how fast electric potential changes along unit of distance. That will give us the electric field. So that is the relationship like backwards. We first introduced electric potential in terms of electric field. And here from these units potential per minute for electric field, we see that electric field is defined how fast electric potential changes along some unit distance. Also, it is important to mention one commonly used unit for electric potential, which is used in atomic physics, also in solid state physics. That is electron volt. So 1 electron volt is energy, like potential energy, which has electric unit electric charge, which is 1.6 10 to minus 19 Coulomb at a potential of 1 volt. So that will be 1.66 10 to minus 19 joule. So in order not to operate with such small numbers, 10 to minus 19 is quite not convenient for practical reasons. This electron volt unit is introduced, and when we deal with very small energies, like potential or kinetic energy of elementary particles, we operate with electron volts. So now let us find the potential difference for the simple case for uniform electric field. Let's say we have electric field vector, point A, point B, and some positive charge. Q moves from point A to point B along electric field vector to point B. So now let's calculate potential difference between points like BA. According to previous definition, which we introduced on previous slides, that will be minus integral from point A to point B, scalar product of electric field vector and displacement vector. Scalar product, in our case, since displacement vector is parallel to electric field vector, we can write minus integral from A to B. Here, E, ds, magnitudes of these vectors, times cosinus 0. There is no angle between them. Cosinus 0 is unity, so we end up with minus integral from A to B, E times ds. So assuming, as we mentioned at the beginning, that electric field is constant, we can place it out from the integral, and for potential difference delta BA, can calculate minus E integral from A to B ds. And that is this integral from A to B is nothing else as the distance d, which this electric charge traveled from point A to point B. So that will be minus E times this distance d. So here, this minus shows us that electric potential at the point B is lower than electric potential at point A. So we also wrote before that dVBA is equal to VB minus VA. If this guy is negative, means that VB is smaller than VA. So if we consider a system with a positive charge and electric field, then the electric potential and electric potential energy of the system will decrease with the electric potential energy of the system electric field charge, a positive charge, will decrease when this charge will move in the direction of the electric field. So while moving in the direction of the field, positive charge moving in the direction of the field, the potential energy of this system, electric field, and positive charge will decrease as much as this charge will continue to move along the field. So another option which has to be considered when electric charge is moving not in parallel to electric field, like uniform electric field vector, but at some angle. So that also should be discussed. So let's say we have uniform electric field vector, and we have point A and point B. So this is the displacement vector, S vector. And here is some angle theta, which is the angle between the displacement vector and electric field vector. So when we want to calculate how will change potential between what is like potential difference between point A and point B in such configuration, delta V, difference in potential, is equal to minus integral from A to B, electric field vector, displacement vector. Here we have scalar product, don't forget about this. So we need to take into account their orientation, assuming that electric field vector is constant. So we take this out, then we have scalar product with the integral from A to B of ds vector. This integral will give us also a vector, and that will be E vector scalar product capital S vector, which is the displacement vector between points A and B. So that in its turn will be equal to electric field, now not vector, just magnitude, times magnitude of the displacement vector times cosinus of this angle theta between electric field vector and displacement vector. What is important here, that this product S times cosinus theta, that is this projection of displacement vector on the direction of electric field vector. Let's mark this projection as D. So we can write here, oh, I forgot here these minuses. It will be equal to minus E times D again. This D is displaced like a component of displacement vector in the direction of the electric field vector. So when we deal with change of potential in electric field, what matters only that component of displacement vector, which is aligned in parallel to electric field vector. Automatically, that means that if we draw a plane, it's in such cross section, some plane perpendicular to electric field vectors, this plane will give us positions of equal potentials, means in each of these points of cross sections between electric field vectors of uniform electric field and this plane perpendicular to electric field vectors, electric potential will be equal. So that surface is called equipotential surface, which defines us the position of equal potentials for a given electric field. It can be different shape surface. So in this particular case, it's just a plane because electric field is uniform. However, if we have some other configurations of electric field, means obviously that these equipotential surfaces will have different shapes, but all of them will show us positions of points with equal potentials. So now let us consider one example when we have some conversion of potential electric potential energy into kinetic energy. So let's consider some plates which are positively and negatively charged, and some positive charge located in between these plates at some point A. Initially, its velocity VA at point A is equal to 0. Then we let this charge to move from point A to point B. This is new position of this charge. Keep in mind that electric field between two plates aligned like this is uniform field with this orientation from positively charged plate to negative charge. And the distance between this point A and point B is D. So in this case, displacement vector is parallel to electric field vector. Distance is given, and we want to determine how this potential difference will between points and A and B will result in change of potential and kinetic energy of this electric charge. Let's call it charge Q. So we know that potential difference will be given as minus E times D. And we also know that there should be some conservation of energy. Means that change in kinetic energy plus change in potential energy should be equal to 0. So what is change in kinetic energy? So since there will be some electric force acting on this charge, positive charge, in the direction of electric field from positive to negative plate, when it moves from point A to point B, this force will perform some work, and that will result in increase of the speed of this electric charge. So that's why we can write m, mass of the charge, let's call it mq, times some speed v squared divided by 2. That is kinetic energy, resultant kinetic energy of this charge at point B. So here we can write that there will be VB is equal to B. However, this is total kinetic energy at point B. So we need to find the difference, the change of kinetic energy. Means that we need to subtract initial kinetic energy. Initial kinetic energy was 0 because this velocity vector at point A was 0. So we put here 0. Then we come back to potential energy, and that is change of potential energy. That will be Q times delta V, as we discussed previously. And this should be equal to 0. According to this equation, we can write that, let's do it on the next slide, mq, mass of this charge, times v squared divided by 2 is equal to minus q times delta v. So from here, we can express the speed of the gain speed of this electric charge at point B. That will be square root minus 2q times delta V divided by mass of this charge, and delta V, change of potential, can be substituted by minus E times D. So if we do that, we get rid of this minus and the square root. That will be 2 times Q times E D divided by MQ. Oh, sorry, not G, but Q. So here we see the expression for the speed, and it is clear that the larger electric field, like stronger electric field between these plates, the larger electric charge, and the larger distance it traveled between point A and B, that all will result in larger speed. And in the denominator, obviously, the heavier this charge is, the slower will be this charge at point B, because it will be more difficult to accelerate such electric charge in given electric field. So with this, we can summarize this introduction of concept of electric potential and electric potential energy. So the key message here, we need to distinguish that electric potential is defined only by source electric charge and electric field, which is created by this source charge. In its turn, when we deal with potential energy, we also need to introduce test electric charge, provide information about test electric charge, and this electric potential energy is always considered in the system of electric field test electric charge. They cannot be considered separately without each other. So if you have any questions, you're welcome. Again, sorry for that interruption. Hope that will not be happening in the future. So we will continue our discussions on Wednesday. Hope that to see all you there. Take care and have a good day.
Thank you.
Thank
Nice
you.
day too.
Thank you.
Goodbye.
Goodbye.
Yeah,
Bye.
you're welcome.
Goodbye.
Bye bye. Take care.